All right, so we're going to talk about directional derivatives. And just to go back to something we've studied before when we did partial derivatives a couple of meetings ago, I believe, I used this equation, f of x y equals 9 minus x squared minus y squared, because it resembles a mountain with a peak right over the z-axis. It's an upside down paraboloid. And if you recall, one of the ways I like to introduce partial derivatives is imagining you're on the side of this mountain at this point 1, 2, your z value would be 4 if you plug that into your function. And do you remember I said, well, imagine you're right here on the surface of the mountain and you twisted your ankle and you need to get down to the ground level, the XY plane, let's say, that's where the bottom of the mountain is. And if you recall, I gave you a choice. I said, you could either at this point face yourself towards the positive x-axis and start to walk down the mountain, right? You could, so like this point, if I had to draw it directly underneath, it would be like right here. But you could go in the positive x direction and you'd be traveling down like the side, it would look like a parabola, right? You would go down this way. And that would be parallel to the x-axis. And the slope that you would experience right at the beginning, that's exactly what we meant by the partial derivative with respect to x. Because you'd be moving in the x direction, not changing your y value. Your y value would stay the same. Then we said, well, what if you face the positive y-axis and move down the mountain that way? That would also be a parabola. Maybe I could try to do this. I have to go parallel. So you'd be like going down a parabola like this to get to the bottom here. And the slope along this path would be given by your partial derivative with respect to y. And to help see this now, because it's hard, this is a three-dimensional graph, but sometimes that's hard to see what's going on. So that would be kind of like, if you can imagine a top view of this mountain, if you were up in a helicopter looking straight over the z-axis, what you would see, you wouldn't even see the z-axis if you were directly above it. But let's say this level curve in red was highlighted, you would see this level curve. If you're looking at it from above, you can't capture height, right? All you're going to really see is x and y. You're not going to see any up and down because you're looking at it from above. So the equivalent of moving in the x direction would be like right here. If you started hiking down this mountain in the x direction, here would be, this is what I would see up in a helicopter. I'd see you moving like this, right? And the slope in this direction would be given by f sub x, would give you your slope. If you moved in the positive y direction right here, that would be moving this direction, and that slope would be given by f sub y. I don't remember if I asked this question, but I will now. How many people feel it's kind of limiting? I mean, the truth is, if you were at this point on the mountain here, why should you be confined to just moving in the x direction or the y direction? Why can't you pick any direction, right? How about something in between to get down to the bottom of the mountain? So now we're going to talk about how you would go about then finding that slope if you did that. So this is called a directional derivative. Hopefully now you've sketched a picture. And just, yeah, what we just summarizing what we just did, your slope in the x direction would be given by let's just say f sub x. And your partial derivative of that is negative 2x, because y is constant. If I evaluate that at 1, 2, that's going to give me negative 2. And if I want to find my slope in the y direction, that would be given by f sub y, which is negative 2y, evaluated at the same point. This time is going to be negative 2 times 2, so it's negative 4. So then here's now, we're going to allow ourselves, what if we wanted to find the slope in some other direction other than just the x direction? And so one way you can specify direction, we know, is with a vector, right? 2i plus 3j is will point in a certain direction, at least in terms of x and y. By the way, this I had to get over this when I was first, many years ago, relearning this multivariable calculus. I had to wrap my head around this idea. Isn't it true? Go back to this picture. If you're on the side of the mountain and you're going to choose a direction to walk in, don't you agree? The direction you walk in it's just X and Y, right? Like you could say, I'm going to go east or north or northeast. Now, it is true, if you actually start walking in that direction, your elevation will change, right? You might go down or you might go up. But in terms of direction, it's just X and Y. That's which direction you're going to face, and then you're going to move, okay? So that vector 2i plus 3j, if I were to plot it here, 2i plus 3j, that would maybe be pointing somewhere like in this direction. I want to move in that direction. This is, how about I write that just in this form? 2, 3 is the direction I want to move in. Now, obviously, you can kind of tell from here, that kind of splits the difference between X and Y. So we're going to be moving, somewhere. We're probably going to be going like down this parabola right here. We're going to be going downhill, right? You would expect you're going to go downhill that way. But we want to find that slope. Okay, so direction, you just need an I and a J, or an X and a Y component. Now, for the purposes here, I've said this before, that a lot of times, even though a vector inherently gives a direction, 2i plus 3j is a vector that points sort of northeast. It's very customary to make something a unit vector. We want to unitize this. Whenever someone specifies a direction, oftentimes we want it as a unit vector. Remember how to do that. You just need to divide this by the magnitude of v. The magnitude of v is the square root of 2 squared plus 3 squared, which is root 13. So this as a unit vector is 2 over root 13, 3 over root 13. So this boils down to a formula, but I want to give you a little insight to where this formula comes from. Let me give you the directions first, and then we'll go back to the graph. So how we're going to go about doing this is we're going to parameterize a line, a three-dimensional, well, no, right now a two-dimensional line, sorry, through our point 1, 2 in the direction of our vector that we want to move in. Okay, so meaning I want to find the equation of a line that's going in this direction that I know passes through my point 1, 2, and it's in the same direction. And you may recall, like, you could write this as a vector, obviously, but if one way to write the equation of a line is in parametric form. I know my line has to pass through the point 1, 2. And if it's moving in this direction, then I could use this as like kind of my direction coefficient for x. So this would be 2 over root 13 times t. And for y, it's moving in the direction of 3 over root 13 times t. I'll just draw another. It'll look as pretty. So what we've done basically here is we found the equation of the line. We'll call this line L. That is, as we're moving down the mountain, we're going to be moving along this line, right? Because this is the direction we want to move in. We're going to move along that line. So what we want to know, what we're interested in is how steep is this going to be, right? In other words, we want to know what our derivative is in that direction, in the direction of our vector u, which we've parameterized as a line L. And so here's how this works. It involves the chain rule. I want to find the rate of change of f of x, y. That's the derivative, basically. This is the derivative. So that's what gives us the rate of change or the slope, right? In the direction of my vector u, which means in the direction of that line. And so notations, most of you have seen this, I think, maybe a few of you haven't gotten here yet, but this is d, the derivative of my function in the direction of u. That's a little subscript. I didn't do a good job writing that. The derivative of my function in the direction of u. It looks like Duff. Okay. So here's how we can get it. My function, remember my function was, I should write this down. Where was my function? My function was 9 minus x squared minus y squared. My function is a function of x and y. But if I'm moving along this line L, then I have x and y written in terms of t, don't I? Both x and y are now functions of t, at least along that line L. So what would the derivative say? I want to find the derivative of my function. I want to find out how much I change for each unit of t. According to my chain rule, to find the derivative of f with respect to t, I'm going to need my partial derivative of f with respect to x times dx dt plus another path here, my partial derivative of f with respect to y times dy dt. So this is why we needed to study the chain rule before we got this section to this section. And then to make this, this is actually it, this will give it to you, but to make this a nice, tidy formula, what we can do is creatively think of this. What does this remind you of? Something we've done earlier, when you do something times something plus something times something. In terms of vectors, doesn't that sound like a dot product? Right? When you do a dot product, you're multiplying two numbers and then adding the other two numbers. So this could be thought of as the dot product of your partial derivative of a vector made up of your partial derivative with respect to x, your partial derivative with respect to y, times dx dt, dy dt. But here's what I wanted to point out. What is dx dt? What is dx dt in this case? The derivative of x with respect to t is just 2 over root 13, isn't it? This is just 2 over root 13. And likewise, the derivative of y with respect to t is 3 over root 13. So I'm going to put these values in. Which means I can think of my directional derivative as the dot product between two vectors. This vector right here, which is made up of your two partial derivatives, we're going to give a special name. We're going to call this the gradient of f. Upside down triangle. This is read the gradient. It's a vector. Oh, can't see that though. There we go. And even though this is dx dt, dy dt, you can see that when I took the derivative, that just was my unit vector, huh? That was the direction I wanted to move in as a unit vector. So this is just u. And I'll write this out again. This means this is the derivative of f in the direction of u. One of the, I know some people have been working on homework on this, and it's kind of frustrating because they'll give you a function and they'll tell you a vector that they want to move the direction in, and they'll write it as u, but it's not a unit vector. This needs to be a unit vector. For this to work. And so this is how we're going to get our derivatives now. We can pick any direction. So for our problem, we actually already worked out, if you think about it, our gradient vector is made up of our two partial derivatives evaluated at our particular point. And we already did that. We got -2, -4. At 1, 2, our gradient vector is -2, -4. This was our gradient. And we have our unit vector being 2 over root 13, 3 over root 13. So if I do the dot product, it's just going to be -2 times 2 over root 13. That is -4 over root 13. Plus -4 times 3. That's actually minus 12 over root 13. So I get an answer of -16 over root 13. And this would be, so why is it negative? This negative is okay in the context here. Again, it's not always mountains and stuff, but the negative means we're going down, right? F is decreasing, or you could think of it as we're going downhill. And that's your slope. You know, you could talk about a slope of a ramp being like -2 means you're going down 2 over 1. This means you're dropping 16 over root 13, let's say, feet for every foot you move in that direction. It's a slope. All right, let's try this for a different point. So same scenario. Here's our level curve for our mountain. We're at the point 1, 2. What we just did was see what happened if we move this way. Now I want to move in the direction of the vector -3, +1. I'm actually thinking maybe let's make this -3, -1. Let's make it -3, -1. Because that vector, if you kind of imagine it right here, that would be a vector that goes 3 units to the left, 1 unit down. So this vector might look something like this. This is our vector v is moving kind of in this direction. -3, -1. So I'm moving. So what do you, before we even do the problem, what would you suspect? That's why I like to start with this particular problem, because we can visualize. You won't always be able to do that if I give you some random function. Remember that the top of the mountain, the peak of the mountain, is the origin. So what kind of a slope would you expect here, right? The peak is right here. I'm not moving straight to the peak. I'm moving kind of, in other words, do you think you're going to be going uphill or downhill? How many people think it's reasonable you might be going uphill now, right? Since you're going at least closer to the top of the mountain than away from the summit, right? You're not going this way here. So now we've already worked out our gradient. Because we're at the same point, our gradient we can still keep. It's -2, -4. So my slope in this direction is the gradient dotted with u. Okay, so now what do I have to do here? This is a vector, but I need to unitize this vector. I need to make it a unit vector. And remember, that's not too hard to do, because if I find the magnitude of v, you can almost do that in your head. It's just the square root of each part squared. So I think that's going to give me root 10. So then I'd be dotting -2, -4 with my new unit vector being -3 over root 10, -1 over root 10. And now I get -2 times -3, 6 over root 10. This is going to be +2 plus 4 over root 10. So I end up getting, as expected, a positive slope. Now, an interesting question, I think, would be, if I was at this same point, 1, 2, on the side of my mountain, I might want to know what direction would I want to move in so that I get the steepest slope. The direction of steepest ascent means uphill, right? Which direction would you face that would carry you up the steepest incline? Another way to describe it is your max derivative, right? Your max derivative, you're going to get a positive, the biggest possible positive slope. Okay. Well, let's see if we can figure this out just intuitively. Let me remind you of the equation of, or the equation, the graph of our mountain is this. This point 1, 2 is right here. We know the peak of the mountain is right here over the origin, right? Right over here at X and Y is 0. So the summit's right here. How many people think it's reasonable for this mountain, since it's nice and symmetrical, to believe that if you wanted to climb in the steepest way from here, you'd probably want to move directly towards the summit. You'd probably want to go this way, right? This is the top. Yes, we did find the gradient. Now I've got some more examples. I'll get away from this particular mountain in a minute and we'll do another example. So what is this as a vector? What is this as a vector? Well, let's see. To get from 1, 2 to the origin, right? This is 0, 0. You'd have to go backwards 1 and down 2. So it appears to be, I'll put direction of max derivative appears to be in the direction of, let me call this V, -1, -2. Which if I rationalize, if I unitize this, okay, I'm hoping by now you can do this in your head. The square root of this square plus this square would be 1, that would be root 5. So this would be -1 over root 5, 2 over root 5, if I wrote it as a unit vector. Now we're using our intuition. That seems to be the steepest possible slope, right? But we can confirm our intuition. We can confirm our intuition, and that's what we're going to do right here. I'm going to fill in a little bit more here. If I wanted to know my maximum directional derivative, and my formula is the gradient of f dotted with u, let's go back to the definition of the dot product. Remember that from 12.2, I think it was. The definition of a dot product of two vectors is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So if the gradient, which we know is made up of our two partial derivatives, is a vector pointing in one direction, and u is the direction we're interested in finding the slope, right? That's the relationship between the two. there's an angle between them. But if we want to find the maximum, let's think about what's the biggest this part could actually come out to be. Well, the magnitude of the gradient, I know I've been using two absolute values sometimes, so maybe I'll do that so it's not confusing. The magnitude of the gradient is whatever it's going to be, right? It depends on the numbers, okay? But this you don't need to guess. What is the magnitude of a unit vector? That's supposed to be an easy question. It is 1, right? By definition, this has to be 1, so that can't be changed. So the only other thing that could change besides this is the cosine of theta. And what's the maximum value for the cosine of theta? The maximum value you could ever get out of a sine or a cosine is also 1, which is going to happen when theta is equal to, in other words, for what angle is cosine equal to 1? It's equal to 0. It's equal to 0. So this tells us something. Actually, two facts. This says if I want to find my maximum directional derivative, the direction I should be moving in, what this is saying is the angle between the gradient and u should be 0, right? So I'll put, so to find my maximum derivative, we should move, oh, I've got it right here. Oh, well, that's okay. Move in the direction of the gradient vector itself, right? If theta is 0, that means the direction you should move in, you should be this direction, should be in the same direction as your gradient vector, right? Because theta would have to be 0. Okay, so this brings up actually two important facts about the gradient vector. The gradient vector is a super, super useful vector that we're going to use, of course, for this quarter and lots of the time in 21D. We're going to be referring to the gradient vector all the time. The gradient vector always itself, just that vector, points in the direction of, we can call it steepest ascent. How about steepest increase? There's another way to put it. I'm trying to give you all the different ways of f. In other words, my maximum directional derivative, steepest increase of f. These are all synonyms for the same thing. Now, the other thing we learn is, okay, to get the maximum directional derivative, this is going to be 1, this is going to be 1. So what would my actual derivative be? If this is 1 and this is 1, my actual final answer here would just end up being the magnitude of the gradient. And the magnitude of the gradient literally equals my maximum derivative, directional derivative. Very, very important facts. So let's go back up here and check our intuition. Because what we now know, we were guessing that this would have been the direction of steepest ascent, but now we know, maybe a different color here. These things work. Let's try purple. We know the gradient vector should be pointing in the direction of steepest ascent, and we've already calculated our gradient vector several times. That's -2, -4. Notice that if I pull out a 2, do you see that? I mean, no, it's twice as long, but do you see that that's essentially the same? It's the same direction, aren't they? The gradient is pointing in the same direction as v. So we could, the gradient vector itself, we could think of is actually right here too. It's pointing towards the summit. Right there. And what is my maximum slope? My max directional derivative is going to be the magnitude of the gradient vector, which would be the square root of, this was my original gradient vector, so -2 squared 4 plus 16 is root 20. Okay, so what this says, okay, root 20 is about, I don't know, I'm guessing here, let's say 4.5, right? If you're on the side of this mountain, right here, and you were interested in the steepest possible slope, you should face the direction of the gradient, and the slope that you will encounter if you move in that direction, this slope right here, which is the biggest possible slope, the slope there would be root 20. My slope of that line is the square root of 20. I'm going to get into some more examples here in a second with different functions. So, but this, you just can't rush this stuff. I just think it's important to know. Like I said, we're going to be talking about the gradient all throughout 21D. So we need to really have a good understanding of it. Okay, one more question about derivatives with this mountain, and then we'll change gears to a different function here. Once again, at this point 1, 2, on the side of the mountain, now we know the gradient vector is pointing this way, right? It's pointing towards the summit. Here's our gradient vector. That's the steepest possible slope. By the way, I forgot about this because I've seen some of this on the homework. If somebody asks which direction gives you the steepest slope, that would be in the direction of the gradient, the steepest ascent. What if I said, what direction is the direction of steepest descent? I'll put, by the way, direction of steepest descent, meaning you're going downhill. Another way to say that is F is decreasing most rapidly. Well, that makes sense. If this is the steepest incline, right? Your steepest decline would just be the opposite direction, right? That's going to be in the direction opposite of your gradient, the negative. Just turn around, right? If you want to go downhill in the fastest way, just turn around. But the question I wanted to pose here is, what direction should you be moving in so that your derivative is equal to 0? So that you don't get any you're not going up or down. Well, if you think about it, remember this red circle that I've drawn? Going back to the picture, this red circle is what I meant to draw was this level curve. Right, this is the level curve when c equals 4. And by definition, if you move around the level curve, think about the three-dimensional graph, is your elevation going to change? No, right? That's why we call it a level curve. So if you don't want to increase your elevation at all, you should move around the level curve. Well, it's curving, obviously, right? So what that means is right at this point, instantaneously, you should be moving tangent to the level curve. You should be going, you know, I know that's going to curve, but right here, you should go tangent. In other words, wait. Hang on. We can prove this. Get my picture here. So here's my gradient. Here's the direction we want to move in. If we want this directional derivative to come out to be 0, as we discussed before, you can't change this. The magnitude of u is going to come out to be 1. More than likely, unless you get 0 and 0 for your gradient vector, this is going to be not 0, right? This is going to be some positive number. So positive times 1. The only possible way this could come out to be 0 is if this equals 0, right? Cosine theta equals 0. And when does that happen? That happens when theta is equal to pi over 2. And so what this confirms is, because that must mean that u, the direction you want, this must be u right here. This vector here, or this one, plus or minus u. This would be moving along the level curve. And what this is saying is, to get no change in elevation, your gradient and u need to be perpendicular, right? That needs to be a right angle. And so this is another important property about the gradient vector. At any point on my level curve, if I was at this point on my mountain, my gradient vector would be pointing this way. And it's going to be perpendicular, like my level curve, if I made a tangent line right here, it's always going to be perpendicular to your tangent line. If I was at this point, here's my gradient vector. Perpendicular, did I say to your tangent line? Perpendicular to the level curve. So very important property here. This last property is something you may already inherently know without even realizing it. You might already know this. I think I introduced the idea of a contour map when I was talking about level curves earlier, a few meetings ago, right? You all know what a contour map is. A contour map is like, well, I have an example for you because I told you I was getting excited about this Mount St. Helens thing. Here, let me share my screen. If you're not familiar with this, let me find which one was it though? Oh, no, it is now. Yeah, this is the one. Hang on. Because this is stuff I want to know come April. So here is this is a top view of Mount St. Helens, and you've seen these maps before, surely, right? These little lines are lines of equal elevation, 5,000 feet, there's 6,000 feet, there's 7,000 feet. And these are just nothing more than level curves. It's like slicing the mountain at different elevations, okay? And the blue here, this is the trail. This is the path of my run. But say you wanted, okay, here, check this out. Oh, this is a perfect example. I just pulled this up right before class. See this little trail right here? This red trail at the bottom? What do you think? Is that steep or not steep? I can't see the chat right here, but check this out. From here to here, see how the path goes? Every time it looks like it's crossing each of these level curves almost at a right angle. So I can tell, even without being on this mountain, that is a very steep very steep trail right there to get you to the top here. That is like going up straight up, almost straight up the mountain. Okay, whereas opposed to, see the blue path, this is my path for most of the race. See how I'm kind of following these level curves? I'm not changing it. There is actually quite a bit of elevation change overall, but I'm not like crossing these level curves. And at a steep incline. And so what I was going to say, like with this little picture here, like you would know, like if you, let's say this is a contour map for some peak, and this is where you parked your car and you were going to do a hike to the top. If you want to hike in the steepest possible way, what you should do is every time you cross a level curve, you should cross it perpendicularly. Because as we just learned, the gradient, which is the steepest possible direction of incline, is always perpendicular to your level curve. So you would always want to cross it perpendicularly. This would be the steepest route, steepest. Whereas, as you know, most trails don't do that, right? Most trails, what do? They do little switchbacks, right? They go like this, right? And one of the things you notice is every time there's a level curve, it's not crossing it at a very steep. The more perpendicular you cross it, the more steep it is, right? And so your trails often go like this, you're stretching out the vertical gain over a longer distance. Right. So most people already have an intuitive sense of that. We just haven't talked about it, right? In the terms of vectors. Okay. Let's get away from this mountain here. And now that we've got all the ideas across, these problems really are not that bad. Just stuff you need to know. So here is a function that I'm sure has some three-dimensional graph that probably looks like some mountains and valleys. I have no clue what this looks like. So we won't have the luxury of visualizing it, but we don't need to now. So we're at the point 3, 2. Of course, there's a z value too, which I could find by plugging 3 and 2 in. But it's as simple as this. They will give you a point and they might say, find the slope at this point in the direction of some vector. And this is what I was mentioning before. I don't like that WebWorks does this. Our formula is the gradient dotted with u, but that ain't this, okay? I know that's u, but remember, u has to be a unit vector. So they can call it whatever they want, but this needs to be a unit vector. So that's the first thing I would do is unitize. Unless it's already a unit vector, make sure your vector is a unit vector. So you'd want to divide by the magnitude. Nine plus 16 is 25. Oh, so that's 5. Of course, 3, 4, 5. So then what we really want as our unit vector u is going to be 3/5, 4/5. The other thing we're going to need is our gradient vector, which is made up of your 2 partial derivatives. So that would be the derivative of this with respect to x is just y. Partial derivative of this with respect to y looks like it's x plus 2y. And of course, I do want my gradient evaluated at my point. I want to get numbers here. So at 3, 2 gives me 2, 3 plus 4, 2, 7. And that's it. I can just put this together. My directional derivative is the gradient. I already have the formula there, so I'm just going to do the dot product. It's 2 comma 7 dotted with 3/5, 4/5. Two times 3/5 is 6/5 plus 28/5, 34/5. Okay, so the simplest type question is they'll just say, here's a function, here's a point, find the slope in a direction. They'll give you that. Just, it's really simple calculation. And then they have, so they try to code some things here to get you to think here. Part B says, is there a direction at the same point? So I'm still at the same point at 3, 2. Oh, I wrote it right here. I got to read my own problems. Where the slope is equal to 8. And maybe the thing to think about when you get a question like that is, why would you be asking me a question like that? Why would you be asking me, is there a direction where the slope is 8? Wouldn't there be? Maybe there isn't, right? And so that might get you thinking like, being kind of skeptical. I don't know, maybe there isn't. Well, 8 is a pretty steep slope, right? 8/1, right? Rise over run, 8/1. That's a really steep slope. So what I'm thinking then, if they're asking if there's a place where the slope, a direction where the slope is a really big number like this, what I might want to know is, what is my maximum slope? And how does that compare to 8, right? So that what I'd be thinking in here is, what is my maximum slope? And of course, we know from what we just discussed, that is literally the magnitude of the gradient vector. My gradient vector was 2, 7. The magnitude of that is 2 squared plus 7 squared, 4 plus 49 is root 53, which if I had to estimate even without a calculator, that's 7 point something, huh? And we know now that the gradient, it is not possible at this point. This is the maximum possible slope you could ever get, which means no. The answer is no. So this is less than 8, right? So there is no direction where the slope equals 8. How am I doing here? Oh boy, okay, half an hour. Let's try this. Let's switch gears. So yeah, I mean, there isn't really that much else to this section. You just need to know about the gradient, that it points in the direction of maximum. So yeah, like, so if I had said, here we go. I'll throw in a part C here. Oh, how about this? What direction at 3, 2 gives the biggest decrease of f? Okay, so there's code for, we know that the gradient points in the, gives the direction of the biggest increase in f. So the biggest decrease would be in the direction of the opposite of the gradient. So the answer is the direction opposite of my gradient vector, which would just be equal to the negative of my gradient vector, which is the negative, we already worked that out, 2, 7. So that would be -2, -7. Whoops. if you're doing WebWorks problems, it's really unclear when you're supposed to make something a unit vector or not. Certainly, if you're using the formula for the directional derivative, you want your vector to be a unit vector. But I think I've said this before, it's customary in the world of math and physics that anytime you want to specify a direction, you should make it a unit vector. So I could turn this into a unit vector by dividing by the magnitude here, but it seems like WebWorks is fine with this. So just a note, if it doesn't take this, then maybe it wants a unit vector, which we already have the magnitude as root 53. So you could also make it -2 over root 53, -7 over root 53 as a unit vector. I don't know. It seems like it's just random.